Welcome back. Now that you have the intuition about what is stored memory, what is input vector when we are talking about Hebb's learning, and what is how the patterns can be retrieved conceptually from a weight matrix. Now we can start looking at what is a linear associator. So let me write that down. Linear associator. So Hebb's learning can be applied to several different types of networks, and here we are going to look at just a simple one, which is a linear associator, and we can draw that as follows. So this is the standard input that we have, which is of dimensions r by 1, and let's say this the input p, a vector p of dimensions r by 1, and that we show the arrow to a box W, and that's the weight matrix where we are going to do the dot product of W with P, and this has the shape S by R. The output of that is the net input that goes into a purelin a transfer function such as a purelin, and that can again be drawn as a box as we see here, and then the final output of that is the output of the neuron, which would be of shape S by 1. So this part right here is our linear layer. This part is the input, and the A that we have is equal to, in this case, purelin WP, and this is the linear associator that we are going to talk about. So in here, this output vector A is determined from the input vector P by dotting it with the weight matrix. So we do a dot product of W and P. So how does this work? Imagine that imagine I swap this. Let's say I swap this and say WP is equal to A, just so that it is easier to write. You can write it, W in the matrix form. So W would be something like this: W11, W12, all the way up to W1R. Why? Because the W has the shape S by R, and the next row would be W21, W22, all the way up to W2R, and then down here we have WS1, sorry, this would be WS2, all the way up to WSR, and that's the weight matrix that we have, and that's the one that stores the patterns. The input is the vector P, which is P1, P2, all the way up to PR, and that is of the shape, as we said earlier, it's of the shape R by 1, so it's a column. This is a column vector. This is a matrix, and the output is A1, A2, all the way up to AS, and this A is again a column vector of shape S by 1. So this is also a column vector. So when we perform the dot product, what we would get from this is the W11 dot P1 plus W11 times P1 plus W12 times P2 plus all the way up to W1R times PR. That is equal to A1. Likewise, W21 P1 plus W22 P2 plus all the way up to W2R PR, and that is A2. And finally, if we generalize this, we can write S1 P1 plus W S2 P2 plus all the way up to W SR PR, that is equal to AS. And these equations we can put them as a vector A that would be equal to the same stuff that we have above, that is W11 P1 plus W12 P2 all the way up to W1R PR, W21 P1 plus W22 P2 plus W2R PR R, and finally we have W S1 P1 plus W S2 P2 plus W S SR, and this would be PR. So here we said, yeah, that's the WSR that we have. So this is the A, which is in the vector form, and we can write this as a summarized note in a summarized notation format. We can write um, let's say any specific row. We call that ith row. Let's say ith row. We can say A of I is equal to sigma j is equal to 1 to r w I j p j. Right? So this is the ith row of the weight matrix, and p is the input. So this is sort of the general notation for how to get a particular output for a given input using the weight matrix W. So linear associator, as we said earlier, is an example of associative memory, and the task of such a neural network, which is this one, a linear associator, is to learn the input pairs, learn the pairs of input output vectors. So let's say if we have input, let me change the color here. So if we have the input P as PQ, then it would have a corresponding output A, and let's say the output is TQ. So for each Q that goes up to capital Q, right? So the idea is that if there is a input Q, input PQ, which has a corresponding uh, output TQ, then what we are looking for are these pairs P1 T1, P2 T2, all the way up to PQ uppercase Q, T uppercase Q. And what follows with this is that if we change the input slightly, so if we change the input from PQ by some small value delta, then that will also create a change in the output. So the output then could be output TQ would have something addition to it, which is, let's say it's a epsilon, and that is what the network is try and learn, is to uh, find these to learn these input output vectors. So if we then have a new if we have some new input vector that we would like to find what the output is, we can then put this new input vector into in the dot that with the W to get our output vector, which is going to be t new. And as we talked about this in the previous video, if these are orthogonal, then we would definitely get the exact match if it is there, else we would get some error along with that particular output. So that is the take home message from this particular video, is that uh, a linear associator is something that looks as we see here. It essentially is trying to uh, learn input output pairs and update the W weight matrix accordingly, and it can be written mathematically in this form. Later on in the next video, we'll see how the Hebb's rule works, how the weight matrix is updated in when it sees a new input.